Now for part A in the question, we're asked to find the probability of A dashed, which means not A, given B dashed, and that means not B. So where we have to start is filling in these probabilities on the diagram. So we start in the middle with A intersection B. So that is 0.13 and we put that in the middle. Now the circle on the left represents A and it adds up in total to 0.35. So it means this part on the left must be 0.22 as these two add to be 0.35. Likewise for B, this must be 0.32 as that plus 0.3 adds to be 0.45. Now these three numbers add together to be 0.67, which means that the number that comes outside must be 0.33 to add up to one whole one. Now let's look at the syntax here. We're getting the probability of not A given not B. So not B would be this one here, that's outside B, and that is outside B. So those two values together are what goes on the bottom of our fraction. So we're picking out of 0.22 plus 0.33. That's the bottom of our fraction. Now the top of the fraction means given those, which is not A. Well, the 0.22 is in A, the 0.33 isn't in A. So the 0.33 is our not A given not B. And if we put those into our calculator, that comes up with 3/5. Now part B asks us to explain why the events A and B are not independent. Now if events are independent, the probability of A times the probability of B will equal the probability of A intersection B. So if we try these then, the probability of A is 0.35, and if we multiply that by the probability of B, the probability of B is 0.45. And when we do that on our calculator, we get 0.1575. Now, if we look here, the probability of A intersection B is 0.13. That is different to the probability of A times the probability of B. So as these numbers are different, that's why they are not independent. Looking at 4C, we've now got an extra event, C, added, and we're told that the probability of C is 0.2. We're also told that B and C are independent, so I've got those linked together. So because B and C are independent, we know that the probability of B times the probability of C equals the probability of B intersection C. But we're also told that A and C are mutually exclusive. So that means that the rings for A and C don't overlap at all. So I've drawn the diagram as above. Now where we're going to start off, well, we can put in, let's work out what the probability of B intersection C is, because that's going to be the probability of B times the probability of C. So that's going to be 0.5 times the probability of C is 0.2, and that comes to 0.09. So I'm going to put a 0.09 in there to start. Now, we know that the probability of C is 0.2, so that one then must be 0.11 because these two add to be 0.2. Let's go over to the left because that hasn't really changed. The probability of A intersection B is 0.13. So this one on the left here, as before, is 0.22. Those two add to be 0.35. And all we've got to find is this one missing in the middle of B. So 0.13 plus 0.09 add up to 0.22, and B in total needs to be 0.45, so this one in the middle needs to be 0.23. Now, if we add up 0.22, 0.13, 0.23, 0.09 and 0.11, we get 0.78. So if we take that away from a whole one, the number that goes outside is 0.22. For the final part, 4D, we've got to find the probability of not B union C. So let's take my highlighter. B union C, which probabilities would we have? We'd have that one, that one, that one, and that one. So that's B union C. But we want the opposite to that. We want the inverse. So we want what's left. So the two that aren't highlighted are the 0.22 on the left and the 0.22 outside. So the answer is going to be 0.22 plus 0.22, which comes to 0.44.